You're welcome, our dear student, in this new episode of your program Madrasa على الهوا for primary 6. Today we're going to talk about law of levers. Law of levers. You studied before what is meant by levers, what is meant by the types of levers, but today we're going to talk about law of levers. As you see, my dear student, this is lever. It is from first class lever. Why? Because fulcrum is between effort force and resistance. This is fulcrum, and this in red color is resistance, and this hand represents the effort force. So it is first class lever. As you see, my dear student, there is a distance between the effort force and the fulcrum. This distance is called effort force arm. Effort force arm. And on the other side, there is a distance between fulcrum and the resistance. This distance between fulcrum and resistance is called resistance arm. So we have two terms now. Number one is effort force arm, and number two is resistance arm. Now let's define what's meant by the effort force arm. Effort force arm is the distance between effort force and fulcrum. Again, effort force arm or force arm, the same, is distance between the effort force and fulcrum. And let's define what's meant by resistance arm. In the same way, it is the distance between fulcrum and resistance, or it is the distance between resistance force and fulcrum. So what's meant by effort force arm? It is the distance between effort force and fulcrum. Distance between effort force and fulcrum. What's meant by resistance arm? It is the distance between resistance and fulcrum. Now, any lever conserves effort. Any lever conserves. Conserves here means saves effort when its force arm is longer than a resistance arm. If the effort force arm in this lever is longer than resistance arm, it conserves effort. What's meant by save or conserves effort? That means that you can use small amount of force to remove large amount of resistance. As you see on the monitor, on this data, please. This is a huge rock. Suppose that I wanted to move this huge rock, its resistance. Suppose it is 700 Newton, its weight is 700 Newton. So I need to use what? I need to use crowbar. This is the crowbar. Okay? I have two cases now. First case is to put this rock behind the crowbar in this place. So it's fulcrum. And this is the hand. And this is effort force. Now, as you see, my dear student, the force arm is longer than resistance arm. Okay, let's imagine and discuss if this resistance is 700 Newton. Can I use or do I need to exert effort of 300 Newton? Maybe 500 Newton? Maybe 700 Newton? To move this resistance? Which is suitable answer? If I say 700 Newton, so it doesn't conserve effort. If I say 500 or maybe 300, 700 and 900. 900, no. It used more amount of effort force to remove or to move this small resistance. But if I use 300 Newton to move 700 Newton, it conserves effort. It's supposed to use or to exert 700 Newton to move 700 Newton of resistance. Okay, but here if I put this fulcrum near to resistance, so I will use small amount of effort, force. So the suitable answer is 300. This lever conserves effort. Why? Because effort force arm is longer than resistance arm. On the other side, this is 700 Newton, and this is screw bar. If I put the fulcrum here, and this is my hand to exert effort, do you imagine or can you expect which number of or which amount of effort force I must exert to move this? 300 Newton, 700 Newton, or 900 Newton? If you say 300, that means that it conserves effort. 700, they are equal. 900, that means that you exerted more effort force to remove or to move smaller resistance. I think that a suitable answer will be 900. Why? Because fulcrum is near to what? Near to effort force. So here effort force arm is smaller than or is shorter than the resistance arm. So it doesn't conserve effort. So my dear students, any lever conserves effort when? When its force arm is longer than resistance arm. That means effort force is smaller than resistance force. In this case, here resistance arm is this red in color, is shorter than force arm, so it conserves effort. This man can use a smaller amount of effort to balance, to be balanced with, or to remove or to move this what? This resistance force. As you see, does it conserve effort? Yes, it conserves effort. Why? Because the distance between effort force and fulcrum is longer than the distance between resistance force and fulcrum. Effort force arm is longer than resistance arm. So it conserves effort. It is first class lever. Also first class lever. This represents the effort force, and the red in color the load resistance force, and force arm is equal to resistance arm. So it doesn't conserve effort. If this load is 700 Newton, we must exert 700 Newton to be balanced with it or to move it. This second class lever. So as we see from the first pictures, first class lever sometimes conserves effort, sometimes conserve effort. Why or when? When effort force arm is longer than resistance arm, it conserves effort. But if effort force arm equal to resistance arm, it doesn't conserve effort. If effort force arm is shorter than resistance arm, we need to exert more effort force, more than resistance force. This is second class lever. As you see, this is the load or the resistance in this place, and this is fulcrum, and this is effort force. Here, as you notice, my dear student, that resistance arm is between this load and the fulcrum. It's short distance. But effort force arm from fulcrum to effort force, it's longer distance. So effort force arm is longer than resistance arm, so it conserves effort. Another one, it's not cracker. This is resistance, this is fulcrum, and the distance between fulcrum and resistance is short, but the distance between effort force arm and fulcrum is longer, always longer. Effort force arm in second class levers is always longer than resistance arm. Why? Because the resistance arm is always between the effort force and the fulcrum. So this type of lever, second class lever, always conserve effort. First class lever sometimes conserve effort. Second class lever always conserve effort. Why? Because effort force arm is always longer than resistance arm. But this is the third class lever. Third class lever. Why? Because force, effort force is between resistance and fulcrum. And as you notice, my dear student, here resistance arm is longer than effort force arm. Effort force arm is short, as you see, just this placement or this distance. But effort force arm is short while the resistance arm is longer. That means we must exert more force to move less resistance. It doesn't conserve effort. We have to exert more effort force to move smaller resistance. As you see, these are types, some types of third class lever, tweezers, holder, fishing hook, manual broom. All these types, all these kinds of third class lever can't conserve effort, never conserve effort. Why? Give reason. Because effort force arm in third class lever is always shorter than resistance arm. Shorter than resistance arm. So first class levers sometimes conserve effort. Why? Because sometimes in first class lever, sometimes the effort force arm is longer than resistance arm. Second class lever always conserve effort. Give reason. Because effort force arm is always longer than resistance arm in second class lever. While third class levers never conserve effort. Never conserve effort. Give reason. Third class lever never conserve effort. Because resistance arm in third class lever always longer than effort force arm. That means we have to exert more effort force to move smaller resistance. But now I can ask you, my dear student, give reason for. Nutcracker always conserve effort. Give reason. Nutcracker always conserve effort. Why? Why nutcracker always conserves effort? Because nutcracker from the second class lever, and the second class lever is characterized by that the force arm is always longer than resistance arm. That means we have to exert smaller amount of effort force to move larger amount of resistance. And another question, give reason. The coal holder can't conserve effort. Coal holder doesn't conserve effort. Never conserves effort. Never. Give reason. Because resistance arm is always longer than effort force arm in third class lever. And there is another question here. Although third class levers don't or never conserve effort, but we use them. Why you use coal holder, my dear student? It doesn't conserve effort. It makes you exert more effort force just to carry smaller amount of resistance. But why you use it? Imagine that you wanted to have or to carry small piece of burned coal. Oh, it's dangerous for your hand. It may burn your hand. So you have to carry it with the coal holder. Give reason. Because or to avoid dangers. So we have to use third class levers not to conserve effort but to avoid dangers. And we use tweezers not to conserve effort. It doesn't have mechanical benefit. We don't use them to conserve effort, but just we use them to avoid dangers or to accuracy in performance. Accuracy in performance. We can't pick up small objects from the watch by using hands, by using fingers, but we use tweezers here. Okay, what's meant by law of levers? Look at me, my dear students, and I need to have your attention. Suppose there is a seesaw, and we have 3 seats here, 1, 2, 3, and other 3 seats here. This is number 1, number A, B, C, D, E, F. And the distance between fulcrum and first one is 1 centimeter. And the distance between fulcrum and second is 2 centimeter. And third one is 3 centimeter. Okay. Here is also 1 centimeter, 2 centimeters, and 3 centimeters. Okay. And I have 2 persons. First one is, or 2 objects, 300 Newton, and second is 100 Newton. And I want to have position, have a place, have seat for each one. One of them may be number 1 is on the right, and number 2 is on the left. Where I can put number 1 with 300 Newton in seat A, B, or C. And to be balanced, the two to be balanced, I must put the second one with 100 Newton on D or E or F. Can you imagine, my dear student? Let's imagine together. Let's think together. If you put this, which have 300 Newton here, okay, this side will move down. And can you put the second object with 100 Newton on D? It's not be balanced. Why? Because the same distance here and the same 300 Newton on A at distance 100 centimeter, while 100 is at the same distance. Why? But the first force is 300 here, while the second force is 100 here. It's not be balanced. Sure, it will move down here in the direction of the larger force. No, we can't put it here. But the suitable place here for the 100 is F. Is F. Now it will be balanced. Why? As you see, my dear student, the distance here is 1 centimeter. The force here on the right side is 300 Newton. On the left side, the distance is 3 centimeter, while the force is what? Is 100 Newton. As you notice, my dear student, if we multiply the force times force arm 300 by 1, it will be 300. While we multiply the resistance here, maybe it's a resistance, maybe I can call it effort force. It doesn't matter. 100 Newton times distance times resistance arm, it will be what? It will be 300. Now it's balanced. So now we can deduce what's meant by law of levers. Law of levers states that, as you see on the monitor, law of levers states that effort force times force arm equal resistance times resistance arm. Effort force times force arm equal resistance times resistance arm. So now the two sides of lever are balanced. The two sides are balanced. Not one of them is more, so it will be balanced. Not move in any direction, but will be balanced. So now, according to the questions in the exam, it's a good way to answer the question. I have, as I told you, my dear student, two sides. First one is force times force R. F dot A means force R, abbreviation, equal the other side, resistance times resistance R. So I can put them here in this magic square. F times F dot A equal resistance times R dot A. We have four givens, four values, but you have to notice that force and resistance must be in Newton. Must be in Newton. What about if he gave me mass, not force, but just mass, not resistance, but mass of object? I must convert mass into force. How? Can you remember what we studied in the first term? Weight equal mass times gravity acceleration. Weight equal mass by 10. So if he gave you in the exam the mass of object, not resistance directly, mass times 10, I can get the resistance in Newton. And you have to notice that F dot A, if force arm or resistance arm, may be in centimeter or meter. But if he gave it to you in centimeter, you must find the resistance arm in centimeter. If he gave it to you in meter, so you must find the resistance arm in meter. It doesn't matter if force arm in centimeter or meter, but it's important. If force arm in centimeter, it's very important to have resistance arm in centimeter. They have, or you have to put them in the same unit, maybe centimeter or maybe meter, but the same. The both of them must be in the same unit. So now, if he gave you three of these values and asks you to find the fourth as resistance, how can you find out the resistance? I can say that force times force R, because this is complete side. This side is completed, force and force R, divided resistance R. To get resistance, you must say force by force arm divided resistance arm. Okay? If he asks me to get resistance arm, you must say force times force arm, this is a complete side, divided resistance. Okay? If he asks to get effort force, which side is completed? Resistance and resistance arm. So you have to say resistance times the resistance arm divided force arm. Okay, if he asks to get force arm, which side is completed? Resistance times resistance arm. So you have to say resistance times resistance arm divided force. Okay, let's go in a short break and then we return back to you. Welcome back, my dear students. Now let's go to this problem. The length of the force arm of a third class lever is 5 centimeter. First given is force arm, F dot A is 5 centimeter. And the length of the arm of resistance is 15 centimeter. So resistance arm is 15 centimeter. If the resistance has a value of 300 Newton, the third given is the value of resistance, R equal 300 Newton. Calculate the value of the affecting force. Now, he gave us three givens. First, to solve this problem, we must write the givens first, as F dot A is 5 centimeter, the first one. Second, R dot A is 15 centimeter. R equal 300 Newton. he asks about R dot A. He asks about affecting force F. He needs F. How can I get F? So now let's return back again to our square. F by F dot A equal resistance by R dot A. He needs to get force. So I must write F equal R times R dot A, the complete side, divided F dot A. So here F equal R times R dot A, divided what? Divided F dot A. Okay, R here is 300 Newton times resistance R 15 divided force arm, effort force arm is 5. Now 15 divided 5, 3. 3 times 300, I must write down 0, 0, and 3 times 3, 9. It will be 900. 900 what? What is it? It is force. So force equal 900. 900 what? Newton. 900 Newton. Another trick, my dear students, in another problem, the length of force arm of a first class level is 20 centimeter. Force arm is 20 centimeter. And the length of the arm of resistance, here resistance arm R dot A equal what? Is 5 centimeter. 5 centimeter. If the resistance has value of 300 Newton, resistance equal 300 Newton. Okay, now, even now, there are 3 givens. And the value of affecting force is 60 Newton. F equals 60 Newton. Is it balanced? Now you have to notice, my dear student. If he gave you in the exam 4 givens as you see, force arm, resistance, and effort force, he asks you about, is it balanced or not? Is it balanced or not? If it is balanced, that means the left side equal the right side. That means F times F dot A must be equal resistance times resistance R. If this side equal this side, it means it's balanced. And if it is not, it's not balanced. Let's see. Force equal 60. Force arm times 20. Okay, it will be 1,200. Resistance times resistance R equal. Resistance is what? Resistance here is 300. Resistance arm is 5. So it will be 1,500. Are these values are equal? No, these values are not equal. So it is not, that means it's not balanced. Give reason, it is not balanced. Why? Because force by force arm not equal resistance by resistance arm. Force by force arm not equal resistance by resistance arm. By this point, my dear student, we reached the end of our episode today, and see you next week.